Hello, quick video on normal distribution and its use. The normal distribution is used for continuous data, such as weights or heights. So it's not like we've got the answers are either 1, 2, 3, 4, 5 in integer values, discrete values. Actually, we can have a weight of 7.453 kilograms or a length of 2.75 meters. The probability curve is this blue line here, and that's called a probability density function, a PDF. And if we want to find the probability in a particular range of values, we have to look at the area under the curve, such as in this green area here. We need a lower value and an upper value. So if we were interested in the probability of something being between 60 kilos and 70 kilos, there, and they were the lower and upper values, we would use those values to find the area between them. And the best way of doing this is to use our calculator. So let's use a quick example of how this works. Okay, we go to buy a bag of potatoes at a supermarket, and they have an average weight of 10 kilograms, but of course they're going to vary in weight, aren't they? And we're going to call that use standard deviation of 0.1 to represent that. And like a lot of these continuous variables, they're in this normal distribution. So quite often this is sort of natural world. It's a bit like binomials. So what we're concerned about is, what if our bag weighs less than 9.95 kilograms, say? That would be a concern, wouldn't it, given what we're paying for it? Okay, so let's draw our normal distribution here. So there's our PDF in blue, and we've got a mean of 10 kilograms, standard deviation of 0.1. And we're interested in our probability that the weight is 9.95 or less. So it's that green area under the curve. That's what we are interested in, isn't it? That represents the probability for our PDF. Okay, what's the best way of getting this? Well, we'll get our calculator out. Okay, so menu, we're interested in here, menu, stats, distributions, excuse me, let's get that, distributions, normal, NCD, because that's the one that gives us the area underneath, isn't it? It's a cumulative. Okay, we can put our values into here. Well, notionally the lowest value in real life is 0, but as with a lot of these calculations for the normal, we want to make sure we capture the whole of the tail, so we're going to put just a very large negative number in there. So I'm going to put in, I typically put in 99999 to help me with that. What's our upper value? Well, that's the one we're interested in, our 9.95. So we've defined our range now, haven't we? Upper and lower values. What's the standard deviation? 0.1. What's the mean? 10. And we should just process that, press the calculate button there, and we've got our results. So we've got 3 values on our screen. The top one is the P, that's the probability, and that's 0.3085. Good, so that's what we're looking for. But it's also given us our 2 Z values, and the Z values are effectively the number of standard deviations for the mean of our the lower and upper points. So the lower one there, saying -1 e plus 0.5, that's their way of doing standard form. So that's -1 times 10 to the plus 5. So that's 100,000, isn't it? -100,000. So that's pretty extreme, isn't it? And the other one is our upper value is -0.5, and that's because our 9.95 is half a standard deviation below the mean. There we are. So there's our results, and that's the easiest way to do it in our calculator, isn't it? There we go. So our P was 0.3085, and that's our Z value for 9.95. Okay, let's have a look and see how we can do this with our tables. This is a bit more difficult, and I'll show you the problem we have that makes it more complicated. MEI tables, page 22, gives us our values, and everything is tabulated on the basis of this Z value, so we need to know that. So the Z is the number of standard deviations from the mean, and we calculate that by getting our mean value, sorry, our actual value, 9.95, and we work out how far away it is from the mean, which was 10. So we know that that's so that's minus 0.05 kilograms away from the mean, don't we? And now we want to standardize that in terms of how many standard deviations is that away. Well, we know a standard deviation is 0.1. So minus 0.805 divided by 0.1 gives us minus 0.5 standard deviations. So that's what we're interested in, is that Z value. Okay, let's have a look in the tables and how they work. Here's page 22. What we got is a nice diagram to help us here. Always have a look at that to make sure we're getting the right thing. You're working out the right probabilities. So each of these values in the table is that area there for a particular value of Z. The Z values, having looked down the side, we can see here are tenths in the rows, and going across, that's the hundredths in the columns. So if we were interested in 0.45, we'd be interested in 0.4 on the left hand side, and then the 0.05 in the column here, that's that one there. So our answer would be 0.6736. Okay, so that's how these work. You'll also notice that every one of these values is greater than a half. There we go, because this table is only created for positive values of Z, yeah? So when Z equals 0, well, we've got half of the distribution, so the probability is 0.5. But that gives us a problem for values, Z values below 0, doesn't it? What are we going to do for that? Well, we're going to rely on symmetry, excuse me. And so if I want to find the area for minus 0.5, that's that green area there, the only way for me to do it is to use my complementary probability effectively and do 1 minus my complementary, which is this area here. Yeah, and if I've got minus 0.5 there, then by symmetry I need to find the area plus a 0.5. So let's go back to my table and look that up. So we're interested in this value here, 0.5 and 0, there. There we go. So our value is 0.6915. That's our complementary probability. So we've got to do 1 minus that. And so our result is 0.3085, as we saw from our calculator. As you can see, it's much quicker to get it out of the calculator. Okay, quick summary then. The normal's a continuous distribution with a PDF, probability density function. We use it for continuous variables like length and weight, and it's different from the binomial, which is for discrete values. It's all normalized using this formula here, Z, which is effectively our standard deviations from the mean. So all the time we're finding our actual value, how far away is from the mean, and then turning it into standard deviations. We can use the calculator's NCD function to find this. We have to put in our lower and upper values, as well as our mean and standard deviation. If we've got just a greater than or less than, then we need to put either a lower or upper value to an extreme, because this is a continuous distribution going to infinity. So we either put in plus 999 or minus 999, depending on the circumstances, some really big number to make sure you get all the probability. There we go. I hope that's of use.